everyone, welcome to Lab 2 for Physics 2211. The purpose of this lab was testing and tracking projectile motion and comparing with and without drag in our computational model to the real life model. I found that drag and the real were the closest in similarity, with the without drag being the furthest off. Some important equations that were used during this simulation was the projectile motion equations, specifically to find the velocity in the x and y component, the magnitude of v times sine theta, and then the magnitude of v times cosine theta give us the y component of velocity and the x component of velocity. Then I calculated drag using negative b times the magnitude of velocity squared times v hat to get the drag force, and then the gravitational force was 0, negative mg, 0, with negative mg being mass times gravity in the downward direction. Net force was calculated with F1 plus F2, and then the position update and velocity update formulas were used to calculate the new position of the ball. So the system is the ball, and then the surroundings is the air around it. This first particular part of the code is to find the launch speed for the x and y component, and then also calculating the radian angle, the projectile motion. So I calculated the radian angle by dividing the launch angle by 180 after multiplying it by pi. And then I calculated the velocity in the x component and in the y component with launch speed times cosine the launch radians, and then, or the y component with launch speed times sine launch radians. So then the second part of the code was focusing on calculating the drag force and then also the force of gravity, with F drag being negative b times speed squared times the velocity hat. Then also calculating F gravity, and then adding those together to get the net force, then dividing that by the mass, and then multiplying that by the time to get the updated velocity, and then using that to get the updated position in this line. So the final simulation with drag gave these graphs in this simulation. The final simulation without drag gave these graphs in this simulation. There's not much of a difference if you're just looking at it straight on, but there is a comparison model that will show you that there is actually a very significant difference. So then in Tracker, I used a protractor to calculate the actual launch angle. This was the final data in this particular graph, and then I used this data and cut to when the ball was released from my hand. As you can see in the very beginning, it's not in motion. So I basically cut that particular part out, which I will talk about more in the potential errors. So this is the comparison model. As you can see, the without drag is actually a lot higher and much more different than the with drag and regular data. The with drag and regular data are shown to be very closely together. The with drag just may have had less drag in the computational model than was actually present in real life. However, as you can see, that they are really close versus the without drag one is super far off. So potential errors: poor alignment of the protractor. I could have always done it wrong and then have gotten the wrong launch angle, which would have messed up the speeds for the x and y component. I could have also estimated when the ball had left my hand wrong, so as a result, this could have messed up the initial positions. I could have also mistracked the ball over time. Who knows, I could have selected a different position than I was normally tracking, so maybe I didn't get the middle of the ball. As you could probably tell by this photo, the ball was rather blending into the background, and so it wouldn't be too far off to say I might have mistracked it. And then also identifying the wrong starting point. I could have identified the wrong starting point, which would have messed up the comparison data as well. So speaking about terminal velocity, our ball is not likely to have reached terminal velocity, mostly because it's not fast enough and there was not enough drag in the air. Also, our ball is not very aerodynamic. An experiment that would actually reach terminal velocity is to increase the surface area of the ball, think like a paper airplane, and then also increase the height at which the ball is thrown, so like downstairs. And then what if we threw it straight up? So this would actually hit the ground second, or because it is at a higher angle. This higher angle gives us a theta of 90, and then our sine is equal to 1. Since the sine is greater than the regular angle, our y component of velocity is going to be greater, and then as a result, we are going to see the ball drop down at a much slower rate in comparison due to the position update formula.